Generalization to multivariate data. Given a sample of d-dimensional observations x equals to the set x to the t, where t is starting with index 1 to n, the multivariate kernel density estimator is p hat of x is equals to 1 over n times h to the t times the summations of summing t equals to 1 to n of k of the function of content x minus x to the t divided by h, with the requirement that the integration of k of x dx integrate for all the r to the d is equals to 1. The obvious candidate is the multivariate Gaussian kernel, that is k of u is equals to 1 over the square root of 2 pi to the d times the exponentials of minus the absolute values of u to the square divided by 2. However, here should be applied to using nonparametric estimates in high-dimensional spaces because of the curse of dimensionality. Let us say x is 8-dimensional and we use a histogram with 10 bits per dimension. Then there are 10 to the 8 bins, and unless we have lots of data, most of these bins will be empty and the estimates in there will be 0. In high dimensions, the concept of close also becomes blurry, so one should be careful in choosing h. For example, the use of the Euclidean norm in equation 8.11 implies that the kernel is scaled equally on all dimensions. If the inputs are on different scales, they should be normalized to have the same variance. Still, this does not take correlations into account, and the better results are achieved when the kernel has the same form as the underlying distribution. That is, k of u is equals to 1 over 2 pi to the d over 2 times the absolute values of s to the 1 half in the exponential, then time the exponential functions of the input minus 1 half times u to the transpose times s inverse times u, where s is the sample covariance matrix. This corresponds to using Mahalanobis distance instead of the Euclidean distance. It is also possible to have the distance metric local where s is calculated from instances in the vicinity of x, for example, some k closest instances. Note that s calculated locally may be singular, and the PCA or LDA in the case of classification may be needed. When the inputs are discrete, we can use Hamming distance, which counts the number of non-matching attributes. That is, HD Hamming distance of x and x to the t is equal to the summations of the one function, where the one function is to verify whether xj is equals to xj to the t or not, and also the summation is summing for all index j starting from 1 to d, and where this one function of xj, which is either not equals to xj to the t. If x to xj is not equals to xj to the t, then we reply 1, otherwise reply 0. Now the Hamming distance of x to the t is then used in place of x minus x to the t or x minus x to the t then to the transpose times s to the inverse times x minus x to the t for kernel estimation or for finding the k closest neighbors.